Hello, everybody. Hey, we're going to do a screencastify of this class, and then you'll see it on the resources. But this is one of those lectures where we've got students out there. So I'm going to be asking a lot of questions, and I might go out of the frame. So you just want to listen, and we'll see what's going on. All right, you guys, on a scale of 1 being really easy and 5 being really hard, how would you say this stuff on forces and friction is? And I want you to raise your hand. So if you think it's really hard, raise your hand with 5 fingers up. And if you think it's really easy, raise your hand with 1 finger up. Okay? So I'm getting a 2, a 3, a 5, a 2, a 3, okay, a 2. All right. Now, so what you're going to see is you're going to see some more of this sort of stuff. You're going to have a quiz at the end of the week, and it is going to be essentially just like one of these problems. It's going to be just like one of these problems, and we're going to make one up. Okay, we're going to make one up. So we're going to start with just a box, let's say here, on the ground. All right, Eric, what is the mass of our box? And I just want you to make something up.
Random number.
Just random. 8?
Yeah.
Okay, so we've got 8 kilograms. And Manuel, we're going to have an applied force here to the right. What is that applied force? Just make something up.
7.
Okay, so we're going to have an applied force of 7 newtons to the right. Okay, that's going to be our applied force. Alexis, we're going to have friction, and this is going to have a coefficient of friction of some number between 0 and 1. So like point something. What is our coefficient of friction? And again, you're just making something up. 0.5. Okay, 0.5. So my question to you guys and everyone out there is, will the box move? Will the box move? Okay, and if so, what is its acceleration? Okay, so that's really what the question is. You guys, this is really kind of similar. This is really kind of similar to what the worksheet questions have been, something very similar to this. Now, the first thing we want to do is to draw a free body diagram. Okay? Now, free body diagram, FBD, okay, is we want to write an arrow. We want to draw an arrow in the direction of all of the forces that are acting on our box. And the way I think about it is I want to draw an arrow for everything that touches it, plus gravity, plus friction. I want to draw an arrow for everything that touches it, plus gravity, plus friction. All right. Baby, can you tell me what is touching this box in this hypothetical situation? Friction. I'm gonna keep friction at the end, but friction's definitely going to be part of it. But what's touching it? Okay, you guys. A lot of times in physics, there are simple questions that you're not quite sure of until you realize what they are. Manuel, what's that? You guys, the floor is touching it, right? Now that might seem a little too obvious, right? Of course the ground is touching it, okay? But what do you call the force of the ground acting on an object? No, but it is related to that. Okay, it is related to that. It is also related to gravity, but not quite gravity. Say again? No, that's kind of similar to friction, but you guys, is there a force of gravity acting on me? Right, obvious. Okay. But if gravity is pulling me down, why am I not sinking into the ground? Because the ground is holding me up, right? And that's the ground we're talking about. Is this like a normal situation where I don't sink into the ground? And the answer is yes. So that's my little way of thinking about what that force is, and it's the normal force. You guys, we don't sink into the ground when we're walking around, okay? So the normal force is going to be going straight up from our box, okay? Now, you guys, how would we push this box, or how would we pull this box? Okay, we could do it with our hands or with a string or a spring or something like that, right? So this applied force, we're going to say that the applied force is touching the object, right? So in this case, we're going to have the normal force because the ground is touching it, and we're going to have this applied force because the applied force is something that's touching it. Okay, so those are two out of our four forces that we're talking about in our free body diagram. So the next one is gravity. Okay, what is the force of gravity acting on this object? Okay, you guys. The force of gravity is also known as the weight, and that is equal to its mass times gravity. Okay, so my next question is, what is the weight? What is the weight of that box? What is the weight of that box? The answer is 80. Okay, because the mass is 8, and gravity, the acceleration due to gravity, as you guys no doubt will remember, okay, if I drop this, how much is it going to accelerate? And the answer is 10, which we've talked about before. So we're going to say 8 times 10, and that is going to give us 80. You guys, what are the units? What are the units for force? What are the units for force? You guys, what does that N stand for? 7 what? 7 newtons. You guys, the units for force are newtons, okay? And a newton is equal to a kilogram meter per second squared. So instead of saying kilogram meter per second squared all the time when we're talking about forces, we just call them newtons, okay, because they're named after Sir Isaac Newton. All right? So, you guys, what are the units for the force of gravity? What are the units for force? Weight is an example of a force, but what are the units? Bebe, you just answered that question 48 seconds ago. What are the units for force? Newtons? You guys. Okay, so the units for force are newtons. So what are the units for the force of gravity? Newtons. What are the units for weight? Newtons. What is the units for the normal force? Newtons. What are the units for the force of friction? Newtons. All the forces, no matter what we call them, the standard units are going to be newtons. Okay, and we're going to talk about those standard units kind of from here. You guys, the reason we use standard units is so that we're all speaking the same language. Okay, you guys, I could tell you that my weight was 200 pounds. Okay, but that's not the standard metric units that we use in science. I could tell you that I have a mass of 92 kilograms. That's not my weight, that's my mass, okay? If I said that I had a weight of 920 newtons, then that would be my weight in standard units. Okay, so that's really what we're talking about. So we're gonna have the force of gravity going straight down. Another name for the force of gravity is weight. And in our case here, it's going to be 80 newtons. And then finally, we're going to have a force of friction, okay? In which direction, left, right, up, or down, is the force of friction going to be for this problem? What is going to be the force of friction? Right. To the right is our applied force. So we're going to try to pull it this way. So what is our, which direction is frictional force going to go? Okay, I'm seeing people out there that are pointing to the left, right? Okay, so this right here is our force of friction. Now I want to remind you guys that the force of friction always opposes the motion or potential motion. It always opposes the motion or potential motion, okay? So this we're going to say is an initial velocity of 0. It's just like a box sitting there, all right? Now, if it would move, we're putting 7 newtons to the right, okay? We're saying that if there was a force, okay, it would potentially go to the right. And so the frictional force would be to the left because it's going against potential. Now, if this initial velocity was 10 meters per second, okay, then it would actually be moving, okay? And then our force of friction would be going in the opposite direction of motion. So it's opposite of the motion or potential motion. So we're going to go back to this 0 meters per second. And so in both cases, this frictional force is going to be to the left because our applied force is to the right. Does that make sense? Okay. Now, you guys, when we have kind of all of this stuff up here, it can look kind of confusing. And I'm telling you, in the world of physics, we can have a lot more information put on a picture. So a lot of times we're going to have a free body diagram that's just going to talk about the forces. And so what it might look like is this dot would represent that mass. Instead of drawing a box, we're just going to draw a dot, okay? And then we would have the applied force, the normal force, the force of gravity, also the weight, and the force of friction, okay? Now, for the most part, all of your free body diagrams are going to look like this, okay? Now, we could put in numbers there, okay? If in your notebook, when you're doing a problem and you write it like this and you have your arrows around your box or something, that's going to be fine, right? Because it doesn't really get more complicated than that. Oftentimes we don't have, for example, the initial velocity or the distance or the time, so it becomes fairly simple. So whether you do it like this or do it like that, it doesn't matter. So if I'm looking at your homework and you have it like this or this, it won't matter. Technically, it should look like this, okay? And that's because we're going to separate out all of the forces and make them distinct from other information like distance and angles and things like that. All right? So, do you guys recall what Newton's second law is? What is Newton's second law? Okay, I'm going to remind you that F equals ma. That is essentially Newton's second law. You guys may remember in, I forget what worksheet it is, I think it might have been 6.1 or 6.2, something like that. We had this little thing, had that triangle with F over ma. So if we wanted to know what the force is, we would multiply mass times acceleration. If we wanted to know what the acceleration is, we would take force divided by mass. And if we wanted to know what the mass was, we'd take force divided by acceleration. Now, you guys, we have talked about this before a little bit, but I'm going to add here this little symbol right there, and that is the Greek letter sigma. That is the Greek letter sigma, which means sum, okay? Can you guys tell me what Greek letter that is? What letter is that? You guys, it's pi. That is a Greek letter, okay? But universally, you guys, universally in math and in science, that is the ratio of a circle's circumference to its diameter, okay? You guys, I'm sure, remember that the circumference of a circle is 2 pi r, and the area of a circle is pi r squared. But that's an example of how we use a lot of Greek letters to represent different things in math and science. And this one right here, that sigma, is no different. And this means sum, okay? And in the United States, we typically don't use sum as much as we use the word add. If I asked you to tell me how much money you had, you would add all your money together. You would add it up, okay? And that's a common expression in the United States. If you went to England or the United Kingdom, they would probably say you would sum it all up. You guys you may remember in the beginning of a lot of math classes, they talk about sum and difference. Sum is adding, difference is subtraction. We tend in the United States to use adding and subtracting. Multiplication and division would be the other terms. Okay, so now what we're going to do for this problem right here is we're going to first start out for the sum of the forces in the y direction, the sum of the forces in the y direction, okay? And this y means up and down. It means vertical. And you guys in math, you're going to have the x coordinate and the y coordinate. So the x is the horizontal and the y is the vertical. So we're going to talk about the y direction, okay? Now, if we think of this box in the same way that we can think of this box that's holding up the computer, how much is it accelerating? How much is that box accelerating? 0, because it's not moving. It's not moving, so it's not accelerating. Therefore, the sum of all of our forces, in the y direction is going to be 0. We know that this box, if we just had a box sitting on a table or the ground, it wouldn't be moving up and down, right? It wouldn't be sinking into the ground, and it wouldn't be levitating off of the ground. Therefore, in the y direction, we can say the sum of the forces is equal to 0. You guys, that's not always the case. But for us, for now, that's going to be the case, right? So we can always say in the y direction that the sum of the forces is going to be 0 for us for now, just to kind of make it sort of simple. But this is how we would calculate what the normal force is. What is the normal force? What is that value? And this is how we figure that out. We're going to add up all the forces, and we're going to say the normal force. And I'm going to call the normal force positive because it's going up. And I'm going to subtract the force of gravity because it's going down. And we're going to say that's equal to 0 because the box isn't accelerating up and down. All right? So we're going to say the normal force minus the weight. Now we figured out the weight. We figured out the weight over here, which was mg, which was 80 newtons. And now, how do we get this negative 80 to the other side? Mathematically, algebraically.
Make it positive 80.
Yeah, we're just going to add 80 to both sides. And we're going to say the normal force is equal to positive 80 newtons. Okay? Now, you guys, the normal force is not always equal to the weight. But again, for our purposes right now, it's the normal force is going to be the force of gravity. Okay? So you don't necessarily have to do this calculation to know what the normal force is for us for right now. Okay? So we now know the normal force is 80. All right. I'm going to scoot this over a little bit more here. And now we're going to say the sum of the forces in the x direction. In the x direction is equal to ma. So if we go back to this box here, is this 7 newtons? Is it enough to make it move? And if it does move, how much will it accelerate by? So now we don't know, you guys, right now we don't know if it's going to accelerate. So we're going to keep this, as an ma. Okay? And now we're going to take the sum. We're going to take the sum of all of those forces. Okay? So what is our force to the right? What is our force to the right? 7 newtons, right? Okay. So we're going to take our applied force, which is going to be 7 newtons. Okay. What is our force to the left? What is going to make this thing slow down or potentially not move? What do we call that? What would we call that force to the left? No, weight's going to go up and down. What's that? What does F sub F mean?
Frictional force.
Yeah, it's going to be the frictional force. And I put negative because it's going to oppose the motion. So we're going to say the frictional force, okay? And we don't know what that is, okay? And that's going to equal to 8. We'll say MA, which is equal to 8A. All right, now, you guys, and we haven't brought it up in this lecture yet, but in this past week, we have a formula. We have a formula for the force of friction. Does anyone remember what that force of friction equation is? Okay. The force of friction is equal to mu, this kind of upside down H, or a backwards Y. You guys, that is the Greek letter mu. Okay, so another Greek letter comes into the case, which is mu times the normal force, times the normal force. Force of friction is equal to mu force normal. You guys, do we know what our mu is? And we made one up earlier, and it was 0.5, okay? So that's going to be 0.5. You guys, what is our normal force? Our normal force was 80. So what is 0.5 times 80? 40. Okay, so our force of friction is going to be 40 newtons. And so we can take this and we can plug it in right there. So we're going to say 7 minus 40 is equal to 8a. What is 7 minus 40? Negative 33? That sound right? Okay, so negative 33 is equal to 8a. How do we get a all by itself? How do we get rid of that 8? Not subtract it because it's multiplied, and then we're going to divide it. Okay, so we're going to divide both sides by 8. So on your calculators, tell me what negative 33 divided by 8 is. I believe it should be like 4.125 negative. Did I do that right?
Yeah.
Okay, so our acceleration is equal to negative 4.125. Okay, so we'll just round it to 1.3. You guys, the units for acceleration are meters per second squared. Meters per second squared. Okay? All right. So if we go back to our original problem, is the box going to move? Is the box going to move? And if it does move, what is its acceleration? So let me ask you this. This is kind of a trick question. What is our acceleration? And negative 4.13 is wrong. Our acceleration is 0. Because, now, you guys, for you guys on the video here, this is computers sitting on a box. You guys, if I push on the box with 0.001 newtons, okay? If I am pushing or pulling with a tiny bit of force, is the object going to move? Okay? You guys, if you shift your seats ever so slightly, okay, you kind of push on your seat left or right, or push on your notebook, or push on your Chromebook. If you just barely touch it, is it going to move? Like, when you first start to touch it, is it going to move? And the answer is no, it's not. There's not enough force to overcome friction. There's not enough force to overcome friction. So in this case, we had 7 newtons this way, and we had 40 newtons this way. So if we pulled with 1, it wouldn't move. If we pulled with 7, it wouldn't move. If we pulled with 39 newtons, it would not move. But if we pushed or pulled with just over 40, that's when it would move. Okay? That's when it would move. Now, you guys, if this was already moving, if it was already moving at 10 meters per second, okay, then this value of negative 4.13 would be the acceleration because it was already moving. And that frictional force would be slowing it down. That frictional force would be slowing it down. All right, so that's kind of a trick question. If it's not moving and we want it to move, our applied force has to be greater than our frictional force. Okay, and in this case, it wasn't. All right, so you guys, let's do this. We're going to change here, and instead of saying an applied force of 7, we're going to say 70. We're going to say 70. And now that is obviously more than 40. Okay, so it now will move, and we're going to go back to this, and we're going to say 70, and we're going to redo the math here. All right, so now we can say 70 divided by 40, which would be positive 30. Okay, now, you guys, another way to say that is our net force. After we add everything up, that is our net force. So it's just another way to say after you get everything added up, it's what your net is. If you guys have a part-time job, okay, a lot of times when you get your paycheck, if you make $10, let's say $15 an hour, and you worked for, let's say, 8 hours, that means you earned $120. But when you get your paycheck, it's not going to be $120. It might only be $90. Why would the amount of money that you earned gross, okay, not be what you get in your paycheck? Because taxes are taken out. So all of the money that you get in your paycheck would be your net pay after they take out all of the deductions. And so the same thing here. When we add these two things together, that is another way of saying the net force. Okay, so now we have a net force that's equal to 30. And now we're going to divide by is equal to 8a. So now we're going to divide again both sides by 8. Okay, and we're going to get that looks like it's 3.75. Okay, so our acceleration is going to equal to 3.75. 3.75. And again, that would be meters per second squared. Okay, so if this was 70, we would come up with a question that says, will the box move? And the answer would be yes. What would be its acceleration? And the acceleration would be positive 3.75. If we went back to 7, will the box move? And the answer would be no. And therefore, the acceleration would be 0. Okay? All right, so you're going to see a quiz question like this, okay? And it's going to give you the same setup. Let's say you have an 8-kilogram box sitting on the ground with an applied force of 70 newtons and a coefficient of friction of 0.5. Okay, and the first question is going to be, what is the mass of your box? And the answer is going to be 8 kilograms. Then the next question is going to say, hey, what is the weight? What is the weight of your box? And you would say mg 8 times 10, that would be 80 newtons. Okay, then the next question is going to be, what is your normal force? And you know that the sum of the forces in the y direction is going to be 0. Therefore, the normal force is going to equal to the force of gravity, or the weight, which would be 80 newtons. Okay, and then I'm going to ask you, what is your applied force? 70 newtons. What is your force of friction? Well, now the force of friction, now you're going to have to do a calculation. And now you're going to say force of friction is mu force normal. You know that your mu is 0.5, and you know that your normal force is 80, and you multiply it together, and you know your force of friction is 40 newtons. Now, will the box move? Yes or no? So if we had 70, then the answer would be yes, it would move. And if the answer was, if our applied force was 7, then the answer would be no. Okay, then the next question was going to be, what is the acceleration? And then in this case, if it was 70, it would be 3.75. The tricky question here is, if the answer was no, and we got an answer of negative 4.125 like we had before, if it wasn't moving, then our acceleration would be 0, even though the math was negative 4.125, because the box wasn't moving. If the box was moving, let's say at 10, and I would say what would be the acceleration, then it could be a negative answer. Okay, so you can see in that quiz, that's a lot of the questions are stuff that are coming directly out of the information that I give you to begin with. All right, so what we're going to do is we're going to give you like 3 tries. We're going to give you like 3 tries at this quiz so that you can kind of learn from your mistakes. And so hopefully everyone is going to be able to get 100% on this quiz. All right. So a couple trick questions that are going to be, it's obvious when you know, okay, but a little less so when I first ask you. For example, you guys, what is the weight of the box? Okay, now a lot of people are going to look at this and say, hey, it's 8 kilograms. Okay, but that's not the weight, that's the mass. So you're not going to be fooled, and you're going to know you're just going to multiply it by 10, and the weight is 80. Okay, so here's another sort of tricky question from our brain. Okay, here's the not tricky question. If I'm just standing here, what is my acceleration? What's my acceleration if I'm just standing here? It's 0, right? I'm not moving. So here's the tricky part. I am going to be walking at 10, or let's say at 2 meters per second squared, constant 2 meters per second squared. Okay, what is my acceleration? What is my acceleration if I'm walking at a constant velocity of 2 meters per second? The answer is not 2. The answer is 0. Why is it 0? I'm moving. Remember that acceleration, you guys, acceleration is the change in velocity over time, the change in velocity. Well, if I'm going at a constant 2 meters per second, my velocity is staying the same, and therefore my acceleration is 0. In our brains, up till now, we haven't really made that distinction. So in our brains, our non-physics brains, acceleration means we're moving, like fast, okay? Which we equate to be just moving fast, but they're not the same thing. Remember, acceleration could be when we're slowing down, okay? When we put on the brakes, we're gonna have an acceleration that's going in the negative direction, which is why we're slowing down. We could have an acceleration when we're turning, because remember, Acceleration is the change in velocity, and velocity would be going in a straight line. So if we turn, we're changing the direction, therefore we're changing the velocity. So the way we can accelerate is either go faster, go slower, or turn. Okay, so those are a couple of trick questions. So on this quiz, be careful of those. And a couple easy things, okay, is that our normal force is going to be the same as our weight. The normal force is going to be the same as our weight. Okay, and then you don't have to do this calculation. Okay, you can just go for it, and then that will help you from the math. You guys, again, it's not always the case in physics, but for our purposes right now, that's what it's going to be. Okay. How does that quiz sound to you? If you get like 3 tries at it, you think you can get 100%? Okay. I think you can too. Okay. And that's what we kind of want. Okay. Remember that your grade under assessment is 40% of your grades, and that's kind of where people's grades are kind of lower. So if we give you this with more chances, you should get 100%, and that will help increase your grade. All right. Does anyone have any questions about anything? All right. So what I would like you guys to do, okay, has anyone finished worksheet 8.1, which I think is forces number 5? Anyone worked on that at all? What I would like you guys to do is pull out your Chromebook, go to Schoology under week 8, go to that assignment, and we'll do number 1. We'll do number 1 together. And you're going to see that number 1 looks really similar to it's going to look really similar to this question and the next question. Okay. And I need to find my number 8. All right, I'm going to probably have to ask you guys what that problem is. I think I got it right here. All right. Have you guys all navigated to worksheet 8.1, which is forces number 5, number 1? Okay. So we have a 5 kilogram box, is that right? All right. And you guys, we have a, what is our applied force? What is our applied force in this case? You guys, just so I have it down, it says a 5 kilogram box is being pulled along on a rough table with a force of 10 newtons. Is that what it says? Okay, so I've got that. So what is our applied force then? A 5 kilogram block is being pulled along on a rough table with a force of 10 newtons. So 10 newtons is going to be our applied force, right? Okay, so this is going to be part of our free body diagram. So our applied force is going to be 10 newtons. And it says our frictional force it says our frictional force is going to be 5 newtons. And that is going to oppose that motion, so we know it's going to the left. You guys, what is our force of gravity? Our acceleration due to gravity is 10. That's the g part. But remember, we want weight. You guys, weight is another name for the force of gravity, and it's equal to mg. mg. So if our mass is 5, what is our weight? Okay. You're going to multiply it by the 10, and we're going to get 50. Okay. So this is going to equal to 5 times 10, and that's going to equal to 50 newtons. All right, you guys, what is our normal force? What is our normal force? You guys remember in week number 6 where we did that FET lab where we had the blue team and the red team that were doing that tug of war? When we had an equal force pulling to the left and right, okay, that was called a balanced force. And what was the acceleration in a balanced force?
0.
It was 0. What was the net force? 0. Okay, because they're equal and opposite. So in our case, in this problem right here, we know that this box is not going to sink into the ground or levitate off. So we have a balanced force, which is normal, right? I am not sinking into the ground. I'm normally pulling down and getting pushed up. My weight and the floor are going equal and opposite. So if our weight is 50, our normal force is 50. And again, not always the case in physics, but for us, for right now, our weight and our normal force is going to be the same. So 50-50. So you guys, we have our free body diagram. We have our free body diagram. Okay. So now we want to do the sum of the forces in the x direction. Okay. We really already know the sum of the forces in the y is equal to 0. Okay. And this is going to equal to MA. Okay. So you guys, what force is going to the right? What force is going to the right? Yeah, 10. Okay. So we're going to have 10. What force is going to the left? Frictional force, which is 5. So we're going to have 10 minus 5, which is equal to 5, correct? So 5 newtons. So you guys, we added up all the forces in the x direction. So that's another way of saying the net force. So the net force is 5. Okay? Now that is going to equal to MA. You guys, what is the mass? What's the value for the mass? 5 kilograms. So, you guys, what is the acceleration? What is the acceleration? We want to get the A out algebraically. We want to get it all by itself. So how do we get rid of this 5 kilograms? Divide it by 5. What's 5 divided by 5? 1. Okay. So 1 is equal to our acceleration. 1 is equal to our acceleration. You guys, what are the units? What are the units for acceleration? Meters per second squared. You guys, I would suggest that you memorize that. Okay, but I want to kind of explain it in a way that it makes a little more sense. Okay. Acceleration is equal to the change in velocity over time, right? What are the units for velocity or speed? What are the units for velocity or speed? If you're going in your car and I ask you how fast you're going, what would you say? Let's say you were going, you'd say, let's say 55 miles per hour. Okay. Now, in science, we're going to use the standard units, and the standard units is another way to say the metric system. So miles is a distance. What is the metric unit for distance or displacement? What is the unit for distance or displacement? You guys, how long is this? 1 meter. Okay, so our standard unit for distance is meters. What miles per hour? So our standard unit for time in the metric system is not an hour. What's the standard unit? It's seconds. Okay, so right here, the units for velocity would be meters per second. Meters per second. Okay, and you've seen a lot of that. Okay, and the standard for time, again, is seconds. So what we're really doing is saying meters per second per second. Meters per second per second. Now, you guys, if we had a fraction divided by a fraction, let's say we have 1/2 divided by 3/4. 1/2 divided by 3/4. You guys, how do you calculate a fraction divided by a fraction? You guys remember what you do? You guys, as soon as I do this, you will recognize it. We're going to multiply by the reciprocal, or we're going to multiply by the inverse, or we're going to multiply by the flipped fraction that's on the bottom. Does that ring a bell? Okay, so this, let me do this where you can see it a little bit better. Okay, so we're going to have 1/2 divided by 3/4. Okay, so there's our fraction. So I'm going to take this 3/4 and I'm going to flip it over, and I'm going to get 4/3. And then I'm going to multiply, and we're going to get 4/6, which would reduce down to 2/3. Okay, so we're going to multiply by the reciprocal, or the inverse, or the bottom fraction flipped over. Okay, and I know you guys have done that. Okay, but now, you guys, we're going to take this meters per second divided by seconds. So I'm going to take this and I'm going to flip it over, and I'm going to get 1/seconds. Now I multiply meters times 1 is meters, second times second is seconds squared. And that is why the units for acceleration are meters per second squared. All right, ladies and gentlemen, good to see you all, and we will see you. We'll see you next week in person and on the videos and Zoom later. All right.